So welcome to the third lecture using VSEPR and Lewis dots to discover the shapes of molecules. We're finally in a position where we can actually start deciding if molecules are polar or not polar, which of course was the original idea when we started worrying about the shapes, is whether molecules were polar or not polar. So let's consider some of the simple molecules we've seen up till now. Now we can go back and look at several of the molecules we've already done. For the mercury dichloride, the two bonding pairs get as far apart as possible, which gives us a linear molecule, and the two dipoles cancel each other out. In the case of the tin dichloride, however, in addition to the two bonding pairs, we have the lone pair. So there are three pairs of electrons around the tin. Three pairs go into a trigonal planar arrangement, where the angles are all about 120 degrees. But the lone pair is invisible, since it has nothing hanging on it. So we only see the results of the two bonding pairs with the chlorides, and we're getting an angle, and that angle is going to be about 120 degrees, so the tin dichloride is a bent molecule. That means the two dipoles do not point exactly away from each other, so they reinforce each other, so that is a polar molecule. In the boron trichloride, we have three pairs of electrons, and we said three pairs of electrons go into a trigonal planar arrangement, and all the dipoles point away from each other and they cancel. In the case of ammonia, on the other hand, the three bonding pairs are pushed down by the lone pair occupying the fourth position. Four pairs of electrons go into a tetrahedron, and so the dipoles again do not cancel, because they're all pointing up towards the nitrogen. And so once again we get a polar molecule. In the carbon tetrachloride, the four bonding pair get as far apart as possible. We end up with a tetrahedral shape, and the dipoles again all point away from each other and all cancel out. Which brings us back to the water, which also has four pairs of electrons around the oxygen. But in this case, two of them are lone pairs. The four pairs of electrons go into a tetrahedron, but the two pairs are basically invisible, and so again we only see the bonding pairs which have the hydrogens bonded to them. In this case, that angle is going to be about 109 degrees. Again, those two dipoles do not point at each other, so they do not cancel, and so water ends up being a polar molecule. So let's consider some other molecules we've run into, like carbon dioxide and sulfur dioxide. If we look at sulfur dioxide, we have to go through the Lewis dot structure, and we find out that the sulfur ends up with a lone pair, a single bond to one oxygen, a double bond to the other oxygen. So we have four pairs of electrons around the sulfur, and four pairs of electrons would like to go into a tetrahedron. But you have to keep in mind, we said the bonding electrons have a problem. They have to stay between the two atoms they are bonding together. And so the two pairs of electrons that form the double bond to the oxygen don't have any choice about spreading away from each other. They absolutely have to be in the same place. And so although we have four pairs of electrons, we only have three sets of electrons pushing against each other. And three sets of electrons go into a trigonal planar arrangement. And so that's the arrangement of the electrons around the sulfur. But that's not the shape of the molecule. The lone pair is invisible. We only see the sulfur and the two oxygens. And the bond angle between the two oxygens is only going to be about 120 degrees, since it's a trigonal planar arrangement of the electrons. And so the molecule is going to end up being bent. That's the shape of the molecule. And since it is bent, those two dipoles do not point straight away from each other, so they do not cancel, and so the sulfur dioxide is going to be a polar molecule. And this is something to keep in mind anytime we're talking about shapes. Double bonds and triple bonds all occupy one position, as far as the shape goes, because the electrons all have to be together in one spot. For carbon dioxide, we get an even more extreme case. The carbon has two double bonds, one to each oxygen. And so while there are 4 pairs of electrons around the carbon, there is actually only 2 sets of electrons, because they both pairs double bonds have to be between the carbons and the oxygen. And VSEPR says 2 sets of electrons get 180 degrees apart, and therefore the 2 dipoles between the carbon and the oxygens actually point 180 degrees away from each other, and therefore carbon dioxide, unlike the sulfur dioxide, carbon dioxide is in fact going to be a nonpolar molecule. And so we see some general rules for polar and nonpolar molecules. First off, to get polar molecules, you have to have polar bonds. If you have only nonpolar bonds, you don't have any dipoles and you can't get polar molecules. That's why organic compounds made entirely of carbon and hydrogen are always nonpolar molecules regardless of their shape, because there simply aren't any polar bonds. You have to have polar bonds if you're going to get polar molecules. But polar bonds by themselves do not get you polar molecules. If all the electrons around the center atom are doing the same thing, that is, bonding to the same kinds of atoms, then you get a symmetric shape, and all the dipoles will cancel out. It doesn't matter if there's 2, 3, or 4 bonding pairs. If they're arranged symmetrically, they cancel out. In order to get a polar molecule, you have to have polar bonds and something asymmetric about the shape. The most obvious thing that gets you asymmetric shapes, of course, are lone pairs, because that means there's at least one direction in which nothing is pulling. The lone pairs are not pulling on the atoms, and therefore there's no dipole there. And so whatever's pointing in the other direction is not going to get canceled by whatever the lone pair is doing. But that's not the only way you get asymmetric shape. Consider a molecule like methane, CH4. CH4 is obviously going to be a nonpolar molecule because it has no polar bonds. Compounds made of just carbon and hydrogen are always going to be nonpolar molecules since they have no polar bonds. But nonetheless, the carbon has 4 pairs of electrons around it, and they'll go into a tetrahedron. If instead we look at carbon tetrafluoride, again the carbon has 4 bonds around it, and so the electrons go into a tetrahedron. In this case, however, we have polar bonds. Fluorine's much more electronegative than carbon, but because the shape is symmetric, it's a tetrahedron, all those dipoles cancel out. And so even though it has polar bonds, the carbon tetrafluoride is a nonpolar molecule. Which brings us to difluoromethane. That is where 2 of the hydrogens have been replaced with fluorines. The carbon still has 4 pairs of electrons around it, but now 2 of them are to hydrogen and 2 of them are to fluorine. And the fluorines, we just said, are much more electronegative than the carbon, so those bonds have dipoles. The 2 hydrogen bonds don't. So the question is those 2 dipoles going to cancel? Well, in the top drawing, they're pointing 180 degrees away from each other, and so it looks like they would cancel. But in the bottom drawing, they're only 90 degrees away from each other, so it doesn't look like they're going to cancel. So which is it? Are they going to cancel or not? And the reality is, of course, is both those pictures are wrong. This is something we've talked about before. You have to keep in mind the blackboard is flat. It makes everything look flat. None of those angles are 90 or 180 degrees. There's 4 pairs of electrons around the carbon. They're going to be in a tetrahedron. This is a 3-dimensional shape. All those bond angles are going to be about 109 degrees. As you can see, none of those angles are anywhere close to 90 degrees. They're all about 109, because that's the real molecule. It doesn't matter how I draw it on the board. All those angles are 109. None of them are 90s. We can look at some other molecules we've seen before. We did formaldehyde at one point. The oxygen and carbon have a double bond. The two hydrogens each have single bonds around the carbon. So the carbon has 4 pairs of electrons around it. But again, the 2 pairs of electrons that form the double bond have to be between the carbon and the oxygen, and so occupy only one space. So we have 3 pairs of electrons around the carbon. They go into a trigonal planar arrangement. That's an isometric shape, but the oxygen is far more electronegative than the carbon is. The 2 hydrogen to carbon bonds are nonpolar, so there is nothing to cancel. The dipole between the carbon and the oxygen, that's going to be a polar molecule. Sulfur dichloride, you can draw it like it's linear, but it's not. It's bent. It's 4 pairs of electrons. The 4 pairs of electrons are in a tetrahedron. That angle between the 2 chlorines is not 90 or 180 degrees. It's 109 degrees. We've seen this before. And for the phosphorus trichloride, 4 pairs of electrons are going to be in a tetrahedron. The lone pair is invisible. It's a trigonal pyramid arrangement. And so again, that's going to be a polar molecule. So we see the rules to get polar molecules. First, you have to have polar bonds. If there are no polar bonds, it's automatically going to be a nonpolar molecule. But that's not enough. You also have to have asymmetric shape. And the way you get asymmetric shape is if you either have lone pairs on the center atom, or if you have different atoms bonded to the center atom. Different atoms bonded might get you a symmetric arrangement of the electrons, but the different atoms will have different electronegativities, and therefore different dipoles. And even though they point away from each other, they won't exactly cancel. And so in the case of like the carbon, the difluoromethane, it's a symmetric shape, but only the fluorines have dipoles. One does have to be a little careful in applying the rules, though, about asymmetric shape. Lone pairs frequently get you asymmetric shape, but we've seen, for example, like the xenon difluoride, the lone pairs actually all take each other out. You end up with, again, a simple linear shape, and even though the fluorines have dipole moments, they point 180 degrees apart, so that's a nonpolar molecule, even though it has lone pairs. In the same way, phosphorus trichlorine difluoride has isomers. If the 2 fluorines occupy the axial positions and the 3 chlorines occupy the equatorial positions, all their dipoles will in fact cancel out. You have asymmetric shape. And therefore it's a nonpolar molecule. Even though it has different atoms bonded to the center atom, they still cancel. On the other hand, where the 2 fluorines take equatorial positions, the 2 chlorines in the axial positions cancel, but the fluorines are more electronegative than the chlorine is, and so their dipoles will not be canceled by the chlorine's dipole. So in that variation, we get a polar molecule. So this is important to keep in mind. You can't go by simple rules. You have to know what the arrangement of the atoms around the center atom are to tell if it's polar or not polar. That brings us to the end of the chapter on molecular shape, structure, polar and nonpolar molecules. The homework is due on Wednesday. I'm going to have to mail you the next chapter, so expect to receive another chapter in the next couple of days. Also, included with that chapter will be the midterm test.